So we have just completed partial differentiation, that is finding derivatives of functions of several variables. Now we're going into integration. All right? Finding the integrals of functions of several variables. If it's a function of two variables, then you'll have a double integral. If it's a function of three variables, then you'll have a triple integral, and you get the picture. Function of four variables, then you'll have four integrals, and so on. So I'm going to introduce you to the double integrals as the easiest one. And I'm going to start by going back to Calc 2 when we did integration. And we'll start by looking at the definition of the integral in single variable calculus in order for us to understand the definition of the double integral in multivariable calculus. And then I will show you how to find double integrals using that definition. So I don't know if you remember that, but the single integral, in the definition of it involved Riemann sums. Okay, so let's just go back. Recall the definition of the integral, that there should not be double integral. Here's a typo, remove double. Recall the definition of the integral from single variable calculus. So let's look at the definition. And it said here, let y equals f of x be a function that is positive and continuous on an interval ab. And remember, the definite integral of f of x from a to b is the area. Remember that? Is the area under the curve, right, between a and b. So this is how we approximated that area. So this is what we did. So this is all review. So let us say this is the function that you want to integrate, y equals f of x, and it's between a and b. All right, so you want to do that. This is what you want to do, to find the area of. So this was what you did, was that you divided AB into n equal intervals. So I'll not put all of them, okay? Right? And so this A was your x0, this was x1, x2, x3, and so on. And the length of each of these intervals was delta x. And delta x was calculated to be b minus a over n. In other words, the length of the interval over the number of the intervals. So how did we approximate that region? We drew rectangles, okay, whose total area was close to the actual area. So you chose an arbitrary point within the rectangle. It could be the left end point of each rectangle, the right end point, or somewhere in the middle. Okay, so for our purposes, let's use the right end point. So you take the right end of each rectangle and draw the rectangle like this. So that's the concept of Riemann sums, and you continue this way. And then what you do, you find the area of each rectangle and you add them all up. That would be an approximate area. All right? So, but what happens is that if you want to find the actual area, if you increase, if you have more intervals, more rectangles, you will get closer and closer to the actual area. Okay? And so we need to bring in n approaches infinity. So as you get closer and closer to infinity, as the number of intervals get closer and closer to infinity, you get closer to the actual area. And so we come up with the Riemann sum formula. So the definite integral of f from a to b is defined as, so this f of xi times delta x, that's the area of each rectangle, the xi is, say, the right hand endpoint. We sum up the area, that's the summation, and we take the limit as n approaches infinity because we want the number of intervals to approach infinity. So that is what you learned before. Now let's apply that now to what we're doing right now, multivariable calculus. So consider a function of two variables. We will define now the double integral of the function f of xy over the closed rectangle R, which is defined like this. So I am going to draw it. Okay, so let me draw a little figure here. All right, so, oh, I need, let me do that in black. Okay, that's too much. Okay, let's do this here. And then let's do this here. Alright, so let's say this is your surface. Let's do, I don't like that here. So you already have that drawing, but I want to reproduce it, so it's not going to look like yours. It's going to look like mine. And you know, I've told you before, I've confessed that I am not an artist. So this up here is the surface f of xy. Z equals f of xy. And it is over the rectangle R. So and by the way, so in single variable calculus, when you find the definite integral, you will find an area, right? Now, when you're finding the double integral over rectangle, you are finding the volume of this solid. Okay, this entire solid here. Okay. So therefore, how do you find the volume? You have to do that subdivision again. You with me? So just like you did the subdivision for the area, you have to do the subdivision for this entire solid. So what we're going to do first, we are going to subdivide the rectangle. So let's go down a little bit. Okay, so I'm going to partition this is your R here, okay? And this is your X, your Y axis and 0 origin. I am going to partition it into sub-rectangles, okay? So like this. And I'm not going to draw all of them, okay? Just a little picture. Okay. So let's just say, now I forgot to put the intervals. This here is A, this here is B, and this here, let me just go down a little bit here, okay? Drop this down. And here is C, and here is D, okay? So we are going to subdivide it, and so like we did before, this distance here is delta x, and then this distance here is delta y. They do not have to be the same, by the way. And let us just say that the number of intervals here would be m intervals or m divisions, and the number of intervals here, n intervals. Now, what is delta x and what is delta y? You calculate that the same way we did it before. So delta x would be b minus a over m. Delta y would be c minus d over n. It should be the other way around, shouldn't it be? Because d is bigger than c, right? So let's change this to d minus c over n. D minus c over n. And then we will need the area of each of these subrectangles. Okay? And the area, let's call it delta A, which is delta x times delta y. Okay? And so you take that and mentally, I'm not going to draw this. You already have a picture of it and you can see it in front of you. You take the solid and you divide it into these little solids or cuboids, and then you add them up, and then you get a Riemann sum. And this is what it is. The double integral over R. So put your, that's the way we write it. It's over the rectangle R. So you put R below the double integral of f of xy dA. So here, f of xij yij would be, you remember we chose a point earlier on within the interval. So this is the point within the rectangle. So f of this times delta, well, dA is really delta A. So let's change this to delta A. Okay. And then we are summing up all of these. That's why you have a double summation. And then you're finding the limit. This is called a double Riemann sum. Okay. So, let's do some work here. What we're going to do, we're not going to do the limits. We are just going to estimate the volume of the solid by just finding the double summations. It will not be the actual area, right? But I just want to show you how you work this out. And we're not going to do any drawings either, except for possibly the rectangle. Okay, so let's do A. Estimate the volume of the solid that lies below the surface Z equals xy and above the rectangle R, defined by x between 0 and 6 and y between 0 and 4. We want to use a Riemann sum with m equals 3, n equals 2, and take the sample point to be the upper right corner of each square. Okay, the first thing we're going to do is to draw the rectangle. So let's do that. Let me bring this up a bit. So x goes from 0 to 6. So let's say 6 is here. Y goes from 0 to 4. And so draw the rectangle, R. So this is R. Now subdivide. M is 3, so you want 3, let me use blue here. You want 3 divisions here, and n is 2, you want only 2. So you have some subrectangles. Like that. So therefore this is now 2, this is 2, 4, okay? Now the first thing we should do is to find delta x. All right, we want delta x, we want delta y, and then we want delta a. Okay? So delta x would be 6 minus 0 over the number of divisions 3, and that is 2. Delta y would be 4 minus 0 over the number of divisions 2, which is 2. Now, I did the calculation, but I'm sure if you drew it, you could have actually seen from the figure that it's 2 by 2. All right? But I just did it so that you could understand the calculations. And so delta A, that is the area of each of these subrectangles, would be 2 by 2, which is 4. Okay? Now, the surface is z equals xy, so therefore f of xy is xy. Now, the question is telling you the sample point that you're going to use is the upper right-hand corner of each square. All right, so let's put in these points. The upper right-hand corner of each square. So we want this point, this one, this one, this one, this one, this one. So we have 6 points to look at. Any questions so far? Okay, so now let us find the double integral over R of f of xy dA. Okay, so this is the notation that we're going to use for double integrals. Sometimes we'll write something different, but for now, let us use dA. Now, it's only an approximation we are finding, so put approximately. So we have to sum up all of these and multiply by the area, by delta A. Okay, so put some square brackets. Okay, what are we summing? So we're summing the value of the function at each of these points. So f of 2, 2, next point, plus f of 4, 2, plus f of 6, 2, plus f of 2, 4, plus f of 4, 4, plus f of 6, 4, and all of this is times delta A, which is 4. Now let's work that out. So f of 2, 2, plug 2, 2 into the function xy. So this is equal to 4, f of 4, 2, 8, f of 6, 2, 12, f of 2, 4, 8, f of 4, 4, 16, f of 6, 4, 24, times 4. And when you work that out, you get 288. So in other words, the approximate volume of that solid is 288 cubic units. Now let's do that same question, but let's use a different sample point. We are going to use the midpoint of each of the squares. Remember I told you you can use any sample point. So let's use the midpoint of each of these squares, and this is called the midpoint rule. So we need to draw this again on the other page. Let's draw the rectangle again. Zero, 6, 4. We want 3, 1, 2, 2. Okay. And then we already know that, let me just say, we already know that delta A is 4. Let's just write it. And then we know that f of xy is xy. Okay. Now, put in the points for the midpoints here. So these are the 6 points we are going to use. And let me put this as 2, 2, and 4. Okay, so let's do that again. Any questions so far? So the double integral over R of f of xy dA is approximately equal to. So let's put, we want to sum up f of all of these points. So f of, what is this first one here? 1, 1. The one next to it is what? 3, 1. Next to it, plus 5, 1. Now let's go above. The first one above, the one to the left is what? 1, 3. The one next to it is 3, 3. And the last one is 5, 3. And then all of this is times 4. Any questions so far? So let's put that into our function xy for each of these points. So f of 1, 1, that's a 1. The next one is a 3. Next one 5. Next one 3. Next one 9. Next one 15 times 4. And that is equal to 144. Okay. And as you can see, there's a vast difference between this and the last one we did, right? Okay. And of course, if we increase the number of squares or rectangles or subrectangles, you will see that the double integral is going to get approach a certain number, and that would be the actual area. Okay, any questions? So that is the definition. All right, we will not do too much on that. We're going to get down into the real stuff now. So when you're doing those integrals, I will not ask you to use Riemann sums. You need to know how to integrate. Okay? So we are going to start with the simplest sort of the double integral. It is over a rectangle. So put your little r below here. Okay? The simplest sort of a multiple integral is the double integral over a rectangle. That's the simplest it can get. So f of xy dA. All right? And we are going to change this dA in a little bit, but that is the general format of writing it. Let's look at a particular theorem, Fubini's theorem. Very important theorem. Suppose that the function f is continuous on the rectangle R. Then the double integral over R, put your R below here, of f of xy dA is equal to, then you put in your limits. A to B, C to D of f of xy. Now look at, I have changed the dA to dy dx. The order, now note, the A to B goes on the outside as the outermost integral, and that is for the x-axis, so make sure you put dx outside. C to D is on the innermost integral, make sure you put dy inside. Fubini's theorem says that if it is over a rectangle, that function, you're integrating it over a rectangle, you can switch the integrals and switch these. You cannot do that over anything else. Over a rectangle you can. Okay, so you can put dx dy and then switch these limits. Okay? So for double integrals over rectangles, the order of integration is unimportant. I'm sorry for all of these typos here. It's unimportant. It's not important at all. Otherwise, it is important. Okay? Now, any questions so far? Because I'm going to show you how to integrate now. Did you remember how you differentiated, did partial differentiation? If you're partially differentiating with respect to x, you held y constant. Good, and you differentiated. Do the same thing here. If you're integrating, when you're integrating with respect to x, hold the y constant. So think of it as a number and you integrate the x. All right? So let me show you number 1. So this says you're integrating from 0 to 2, 0 to 4 of 3x plus 4y dx dy. You do the innermost integral first. So do that first. So first integrate with respect to x. Okay, so that's equal to, so put your 0 to 2, put your square brackets, and you are ready to integrate. 0 to 2, the outermost integral. Okay, let's go. So you're integrating with respect to x. Be very careful here, okay? What is the integral of 3x with respect to x? 3 over 2x squared. Plus, now look at this 4y. Remember, y is a constant. So what is the integral of this constant with respect to x? 4yx. Great. Put your square brackets. Now put the limits. Remember, these limits are x limits, so I'm going to put x goes from 0 to x equals 4. When you get the hang of that, maybe you will not have to put its x, right? But you're just doing that, so I would advise you to put x. Okay. So substitute 4 first. 4 squared, that's 16. 16 by 3 halves is 24. Plus 16y. So that's 4. And then when you put 0, you get 0. So we don't need that. And then put your dy. And as you can see, we are now back to single variable calculus. Okay? And this is familiar to you. So it's what you have done before. So let's integrate that. Integrate 24 with respect to y. What's that? 24y plus 16y with respect to y. 8y squared from 0 to 2. Substitute. That's 48 plus 2 squared times 8, 32. And 0 gives us 0, so the answer is 80. So what this means is that the volume of the solid comprising of this function 3x plus 4y over the rectangle defined by 0, 2, and 0, 4 is 80. Okay, that's what that means, the volume. Yes?
So is that a 2 by 4 rectangle then?
Well, what do you mean by a 2 by 4 rectangle? I've never heard that term before.
So it would be like 2 units by 4 units?
Yes, the rectangle would be 2 units by 4 units. Very good. Okay, let's do another one. Okay, so we're doing the innermost integral first. So notice we are first going to integrate with respect to y. Okay, so let's go. Put the outermost integral, leave it alone. Put your square brackets. Now integrate x squared y cubed with respect to y. You're integrating the y. Tell me what's that? X squared y to the 4th over 4. Very good. And y goes from 2 to y equals 4 dx. Okay, let's substitute these limits. So put your integral symbol here. Okay, what is this? We want 4 to the 4th over 4. I think that's 64. So that's 64x squared minus, put 2 now, 2 to the 4th over 4. I think that's 4x squared dx subtract. That leaves us with 60x squared dx. So we are now in single variable calculus. Now let's integrate. What is the integral? 20x cubed from negative 2 to 1. Substitute. This is 20 minus, and put negative 2, that's negative 8, that's negative 160, and the answer is 180. Okay, let's try this one. Just hold on, check that you have something to do, or if I should have put do by this. Okay, so that's for me to do, but we can all do it together anyway, because you have your own in a little while. Let's do it. So we first integrate with respect to x, okay? So put the 0 to pi over 2, put your square brackets. So who would like to give me the integral of sine x cosine y with respect to x? Minus cosine x cosine y. Beautiful, because the integral of sine is negative cosine. And x goes from 0 to x equals pi over 2 dy. Okay, so let's substitute now. So put pi over 2, so that's negative cosine pi over 2 cosine y minus, put 0, so that's a minus minus, so that's a plus, cosine 0 cosine y dy. Any questions so far? Now you need to simplify before you can integrate. So let's see what we get here. Cosine pi over 2 is 0, so that goes. Cosine of 0 is 1, so you're just left with cosine y dy. Very nice. What is the integral of cosine y? Anybody? Sine y, 0 to pi over 2. Substitute sine pi over 2 minus sine 0, and sine pi over 2 is 1. Sine 0 is 0, so that is fine. So that's straight integration, right? Now I think we're going to do an application now, right? Remember I told you that when you're finding the double integral over a rectangle, you are finding the volume, right? Of the solid, where the surface is lying over the rectangle. So if you see a question asking you to find volume, don't get confused. It is just a double integral. So look at number 4. Find the volume of the solid that lies under the plane 4x plus 6y minus 2z plus 15 equals 0, and above the rectangle defined by that, x between negative 1 and 2, y between negative 1 and 1. Okay, now to know what we need to integrate, you need a function, f of xy. F of xy will be whatever z is. So in other words, you see that plane, you need to solve for z. Okay? So let's do that. So you have 4x plus 6y minus 2z plus 15 equals 0. So 2z is 4x plus 6y plus 15. And so z is 2x plus 3y plus 15 over 2. And this is equal to f of xy. Okay, so now let's find the volume. So the volume is equal to the double integral of 2x plus 3y plus 15 over 2 with respect to x and y. You remember I told you it's over a rectangle, so you can put dx dy, you can put dy dx, but make sure you put the limits in the right place. Okay, so if I put dx dy, then the x limits must go first. So the x limits are from negative 1 to 2. The y limits from negative 1 to 1. Alright, so we set it up. And then we do what we did before. Any questions? Okay, so let's do that. So remember, we are first integrating with respect to x. Okay, I will stop putting these grouping this because you will get used to it in a little while. Okay, let's do it. One person give me the integral of 2x with respect to x. X squared, good. Plus another person give me the integral of 3y with respect to x. 3yx. And finally, what's the integral of 15 over 2 with respect to x? 15 over 2x. And then x goes from negative 1 to x equals 2 dy. Okay, let's substitute. So put negative 1 to 1, put some parentheses. So put 2 first. So that's 4 plus 6y plus 15. Put that in one pair of parentheses. Minus, open again. Put negative 1, so that's a 1 minus 3y minus 15 over 2 dy. And then when you work all of this out, you will get 51 over 2 plus 9y with respect to y. Okay, let's integrate that. With respect to y, integrate 51 over 2 with respect to y. What's that? 51 over 2y. Integrate 9y with respect to y. What's that? 9 over 2y squared. From negative 1 to 1. Let's work that out. Oops. So put 51 over 2 plus 9 over 2 minus, put minus 1, 51 over 2 plus 9 over 2. Is that 0?
You forgot a negative.
Oh, that, okay, that's what I'm saying. That cannot be 0. Right, so the answer is 51. Thank you. Any questions? Find the volume of the solid in the first octant bounded by x squared plus 2y squared plus z equals 16. The planes x equals 2 and y equals 2. Now, I think I told you that, but let me repeat it again. When we are in 2D, we speak about the first quadrant, right? When we are in 3D, we speak about the first octant. All right? So remember, in 2D, the first quadrant is bounded by the lines x equals 0 and y equals 0, right? The first octant would be bounded by x equals 0 and y equals 0 also. All right? Okay, let's find the volume. So now we have this surface. Let's find what z is. So x squared plus 2y squared plus z equals 16 tells me that z equals 16 minus x squared minus 2y squared. So this is your f of xy. So let's find the volume. So you are finding the double integral of 16 minus x squared minus 2y squared. What are the limits? Can anybody tell me? What do you think they are? 0 to 2 and 0 to 2, right? So you can put dx, dy, dx. It doesn't matter because the limits are the same.
What if they weren't the same?
If they weren't in terms of x equal, then you'd have to choose. You'd have to choose which one you want to put first, whether it's dx or the dy. You can do either one because it's over a rectangle. Okay, so let's integrate. I'm not going to put the grouping anymore. Let's do it. 16, the integral of 16 with respect to x is 16x. Next one, with respect to x, x cubed over 3. Somebody else, the next one with respect to x, 2 1, 2y squared x, and x goes from 0 to x equals 2 dy. Okay, let's substitute. Put 2, that's 32, minus 8 over 3, minus 4y squared. Put 0, you get 0 dy. Okay, we need to simplify this. 32 minus 8 over 3, that's 96 minus 88, which is 88 over 3, minus 4y squared dy. Any questions so far? Let's integrate. What is the integral here, anybody? Next one, 4/3 y cubed from 0 to 2, which is 176 over 3 minus 32 over 3, which equals 48. Okay, so now I think it's your turn. Okay, let's go over it. Let me make the point here again that this integral is the same as if I put it like that, 0 to 2 1 to 4 of the same thing, dx dy. It's the same thing, you get the same answer. And the reason is because it's over a rectangle. How do I know it's over a rectangle? The limits are all constants, all numbers. The next time we're going to do integrals over more general regions, and you're going to see variables here. This means you cannot interchange, okay? So this is equal to the integral from 1 to 4 with respect to y. It is 3x squared y squared minus 2xy from y equals 0 to 2 dx, which is equal to 1 to 4. Put 2 for y, you're going to get 12x squared minus 4x dx. Integrate further, 4x cubed minus 2x squared from 1 to 4. And then when you substitute there, you will get 222. Any questions? Number 7. Find the volume of the solid line under the elliptic paraboloid and above this rectangle. So from the elliptic paraboloid, z is equal to 1 minus x squared over 4 plus y squared over 9, and this is f of xy. And so you're integrating 1 minus x squared over 4 plus y squared over 9.
Would it be minus y squared over 9?
Minus y squared over 9. Yes, I made that same error again.
Dy dx instead of dx dy.
You can use dy dx, you can use dx dy. But make sure that you have the right limits. So if I put dx dy, I'm going to put negative 1 to 1, negative 2 to 2. If you put it as dy dx, then you have to put the negative 2 to 2 on the inside. Okay, let's do the opposite of what's on the board. Okay, so take this out. Okay, so it's dy dx we're doing, right? So negative 2 to 2, negative 1 to 1. Let's work that out. All right, so negative 1 to 1, integrate with respect to y, y minus x squared y over 4 minus y cubed over 27. Y goes from negative 2 to y equals 2 dx. Substitute 2 minus x squared over 2 minus 8 over 27 minus, put negative 2, that's minus 2 plus x squared over 2 plus 8 over 27. Okay, what is this? This is equal to, okay, so that's a 2 plus 2, that's a 4, minus x squared over 2, that is just minus x squared by itself. Minus 8 over 27 minus 8 over 27 is minus 16 over 27 dx. What is 4 minus 16 over 27? 27 by 4 is 108. 108 minus 16 is 92. Is that right? 92 over 27 minus x squared. Are you asleep? Dx. Is it 92 over 27? Because I don't want to. Okay, it's correct. All right. Integrate 92 over 27x minus x cubed over 3 from minus 1 to 1. This is equal to 92 over 27 minus 1/3 minus minus 92 over 27 plus 1/3. And this is equal to 2 of these 92 over 27, so 4. 184 over 27 minus 2/3. Could you work that out for me, please? Make sure we get the right answer.
166 over 27.
166 over 27. What's the question? What's minus 18 over 27?
Subtract 18 from 184 is what you said.
Pardon me?
The 2/3.
Oh, yeah. Is that it? Any questions?